Let's now think about applying energy methods to our two-body system. We have only internal forces, we have only the single force of gravity, and gravity is a conservative force, and so we know that energy for the two-body system must be conserved. Let's take a closer look at this. We will define the specific energy as the total energy of our orbiting body divided by its mass. And that means that we can write this as the sum of the kinetic energy, which is V dot V over 2. And this is, of course, specific kinetic energy because we're scaling everything by the orbiting body mass, plus the potential energy. And the potential here is a function of the position only. Remember that for conservative forces, forces are gradients of scalar potentials, which means that the potential energy can be thought of as negative the integral of the specific force on the body, so that's F scaled by m, dotted into the displacement, this differential operator that we have previously defined. And so we can simplify this by saying E is equal to V squared over 2 minus the integral of the gravitational force on the body over m dotted into its displacement. That force we have already defined. By Newton's law of gravity, it will be equal to negative the gravitational parameter times the orbital radius divided by the norm of the orbital radius cubed. And so if we carry out this integral, we will find, so we have negative mu over scalar r plus mu over some reference r. This second term represents a constant of integration. It is the 0 point of the potential energy, and we get to choose it however will suit our purposes the best. It makes sense for us to just get rid of it, which is why we typically take this r reference to be infinity. So we take this to be infinity, which makes this whole term go to 0. And this is physically consistent with our understanding of gravity because we essentially model gravity as having an effect for all separations, but going to 0 as the separation goes to infinity. And so the 0 point, our reference point, will be taken at an infinite separation. So that is how we finally achieve this expression here. The specific energy is equal to the velocity magnitude squared over 2 minus the gravitational parameter over r. And this is a constant. For closed orbits, we have two turning points, and we have h, the specific angular momentum magnitude, which is equal to r cross v magnitude, and it will be equal to rp vp and ra va. That is the product of the orbital radius magnitude at periapse and orbital velocity magnitude at periapse, and the same thing at apoapse. So we can substitute this into our specific energy expression and write E is equal to, remember that we've already found that the periapse radius is equal to a times 1 minus e, and similarly that the semi-parameter is equal to a times 1 minus e squared, and is also equal to h squared over mu, which is a constant. From this, we solve for the eccentricity as the square root of 1 minus L over A. And we find, putting this all together, that the specific energy can be written as and when the smoke clears from the algebra, this all evaluates to negative the gravitational parameter divided by twice the semi-major axis. Closed orbits have negative specific energy. So circles and ellipses always have negative specific energy. Their semi-major axes are strictly positive quantities, and so this evaluates to a strictly negative quantity because the gravitational parameter is strictly positive. Open orbits have strictly positive energy. And that means that by convention, we define the semi-major axis of hyperbola as negative quantities. And then the parabolic orbits have 0 energy, which is why we often think about the semi-major axis of a parabola as being effectively infinite. So ellipses and circles have positive semi-major axes, hyperbolae have negative semi-major axes, closed orbits have negative specific energy, and open orbits have positive specific energy. Because energy is constant and independent of position and velocity, we can use this to our advantage. And we can rewrite this expression, these pair of expressions, to solve for the velocity squared, which is equal to the gravitational parameter times the quantity 2 over the orbital radius minus 1 over the semi-major axis. And this is sometimes called the Vis-viva equation or the Vis-viva integral. And this is an incredibly useful quantity that we will come back to very, very frequently. A few final notes. For a circular orbit, the radius is equal to the semi-major axis everywhere. And so from the Vis-viva equation, the circular orbit velocity is equal to the square root of mu over r everywhere on the orbit. For a parabolic orbit, a is effectively infinite. And so the parabolic orbit velocity is going to be equal to the square root of 2 mu over r, which is the square root of 2 times the circular orbit velocity. This is also known as the escape velocity because this is the velocity for a given separation at which your orbit goes from closed to open. And so in order to escape the gravitational pull of your original central body, you must be going at or greater than escape velocity. Finally, if we plug in the parafocal frame component form of the velocity that we previously developed into the expression v dot v, what we will find is that r v dot v is equal to r dot squared plus r squared nu dot squared, which is equal to r dot squared plus h squared over r squared. And so our specific energy can be rewritten as r dot squared over 2 plus the potential u of r plus h squared over 2 r squared. We lump these two terms together and call these the effective potential, because this is the only term left that is a derivative-like quantity, and so this is the only velocity-like quantity, even though this term belongs in part to this kinetic energy expression. This is the only thing that is a function of a derivative of position. Everything else is just a function of position and constants. And so if we break things out, as is done in this graph, we get a nice parameterization of what is happening. So here we have the individual components of the effective potential. Here's the negative mu over r line. Here's the h squared over 2r squared line. And here's their sum, the effective potential. We see that the minimum effective potential occurs at the circular orbit. Between that and 0, we have all of the elliptical orbits that have 2 turning points. At 0 exactly, we have the parabolic orbit. And then above this, we have the positive effective energies. And this is where we have the hyperbolic orbits that only have a single turning point. Notice that we now have 7 conserved scalar quantities in our two-body system. We have the specific energy, we have the specific angular momentum vector, and we have the eccentricity vector, which was the constant of integration that we got at the very start of our exploration of the two-body system. Now, these are not all linearly independent. We can see this most clearly by, for example, noting that h dotted into E is equal to 0. And so there's obviously some linear dependence here, and therefore there's not actually 7 independent conserved quantities. We have already showed that E squared, for example, is equal to V squared H squared over mu squared minus 2H squared over mu R plus 1. And that means that we can also write this as equal to twice the specific energy, H squared over mu squared plus 1. We can also differentiate the specific energy and write the scalar derivative of E is equal to, that is 1/2 the gravitational parameter squared over the specific angular momentum squared times the quantity eccentricity squared minus 1. So in actuality, we have 5 independent constants. Recall degrees of freedom of a system. In 3-dimensional space, every particle has 3 degrees of freedom. A system with d degrees of freedom, d DOF, can have at most 2d minus 1 constraints. And the reason for this -1 is that you cannot determine all 2D sets of initial conditions that you would need to integrate the system without some initial time. So you're down by one constraint maximally. So the fact that we have two particles, 6 degrees of freedom, and 5 constraints means that this system has the maximum number of constraints, and this system is known as maximally superintegrable. So Keplerian two-body orbits are maximally superintegrable, which is just another way of saying that they are completely solvable, which is what we've been saying this whole time. These are the only systems in astrodynamics that we can write down all of these cool, complete solutions for. And as we move forward, we will be introducing other systems that are not integrable and that are nowhere near to maximally superintegrable. And we will still be able to tease out some analytical tractability, but never to the extent that we can for the two-body system, which is why we spend so much time on the two-body system.